Non vi ricevo.
Dataset processing. And he will present a project developed under Digisky Company, that is a small company located in Turin, but following some rules or some goals made by the European Space Agency. Please, Luca, the floor is open.
Vi chiedo solo di abilitarmi la condivisione schermo.
Adesso stiamo lavorando con il...
Perfetto. Thank you. Can you see my screen?
Yes, thank you.
Okay. Good evening to all of you. My name is Luca Livolto. I'm a civil and geomatics engineer at Digisky SRL. And today I'll be presenting to you Skymetry, a platform which integrates drones and airplanes acquisitions with satellite imagery. I'll start off briefly from a short video introductory of the platform. I hope you can see it.
Un attimo, stiamo vedendo per il video. We can listen the audio.
You can't hear?
No, we can't hear you.
We can't hear, but we can...
Maybe it's because you are not sharing the audio from your system.
1 second, sorry about that. I'm sorry. I'm sorry you can't hear it.
From the sharing option, you should select condividi audio dal computer if it's in Italian.
Here. Ok. Mostra impostazioni di dispositivo.
Let's try to stop sharing and share it again.
Ok, includi audio di sistema. Sorry about that. I apologize.
You can reload the video.
Just tell me if you can hear something.
Sounds great now.
Skymetry is the world pioneer for advanced aerial monitoring services. Engineers, pilots, and data analysts with years of experience join together to offer you the most competitive solutions for all the activities that can benefit from aerial monitoring, such as design, building, and maintaining infrastructures like roads, railways, and power lines, optimization of crop yields, evaluation of environmental risks, including emergency operations monitoring. Customer requests are easily configured through our online one-stop-shop solution that allows worldwide direct access. Depending on the request, Skymetry staff will plan the mission selecting the appropriate platform, UAVs, planes, or even satellites, and each platform will be equipped with the specific sensors: optical, multispectral, LiDAR. Our global network of certified pilots and aircrafts will provide the closest possible mission-ready team all over the world. Once images have been acquired, Skymetry's data analysts will process them in order to provide maps, pictures, and digital surface models. The final output can be viewed in a VR environment. Skymetry's data are all accurately geo-referenced, allowing the customer to easily inspect power line corridors, assess highway pavement conditions, evaluate railroad conditions, increase crop yields, timely monitoring of critical areas for environmental risk. Skymetry guarantees fast acquisition time, high-resolution geo-reference data, scalable on-demand service, online access, worldwide network of partners in a cost-effective, all-in-one solution. Skymetry, sense your Earth.
So beyond this brief presentation, I'm going to start by introducing the Digisky Company, which arises as one of the fewer Italian leading companies in the Earth observation field executed by aircrafts. For the past 15 years, founded by engineer Paolo Pari and Maurizio Cheli, we have been focusing on the skills and the development of knowledge in the aerial monitoring field for both the environment and also the large infrastructures. Through the development and certification of the Smart Bay platform, it has been possible to embark on our aircraft's several different types of sensors. And furthermore, through the development of the Skymetry platform, we're now capable of managing the mission planning activities, furthermore provide a flight coordination, consent data validation, and generate digital thematic maps with a high level resolution. Under these circumstances, having become one of EASA's approved, Digisky operates on both the national and international context, operating with general aviation aircrafts, fully certified and STC approved. As the Earth observation operations often proceed on three different segments, recently the European Space Agency has defined the Digisky as the satellite's magnifying lens. In such a sense, the aerial acquisitions conducted through aircrafts and drones may fill the gap left behind by satellites and perform integrating and furthermore integrating datums from different sources such as satellite imageries and aerial space maps. It may be possible to plan aerial high-resolution acquisitions on vast areas with limited expenses. As shown by the tabulator data, Digisky fleets may fill the gap left behind by the satellite environments, and furthermore, in particular, due to the EASA certified Smart Bay technology, we may integrate and mount on several general aviation aircraft such as P-92, PA-32s, Cessna 172 or P2002 aircrafts, several different types of technologies. Hereby, we may state that in general, the Smart Bay technology has four main assets, such as a low cost, a simplicity of acquisition, as the pilot may solely operate the technology with no necessity for ground support, a multi-sensor integration allowing to gather different kinds of complementary data in order to enhance and enrich the data set acquired, and furthermore, perform a smart boarding and therefore an agile and rapid mounting without any need to redesign the system for each boardable sensor. Over the past 10 years, the Smart Bay technology has been including photo cameras with gyro stabilization, laser scanners, hypospectral cameras, or furthermore custom sensors upon the clientele's needs. This does not mean that aircraft's acquisitions steal the job of drones acquisitions. We perform as well through our drone unit UAV acquisitions, typically confined to more restricted and smaller areas in terms of vastness. And furthermore, also we perform more punctual inspections through drones, implementing and in a complementary way the aerial acquisitions performed by airplanes. Under these sense, we may therefore state that the major fields of applications on which Digisky focuses are corridor mappings in terms of linear highways, railways, roads, infrastructures, as well as conducts. Furthermore, we have been operating on a national scale for what concerns the hydrogeological monitoring, inspecting catchments, river networks, dams, and furthermore glaciers. We have had some applications in the forestry and agricultural field, as well as the urban and industrial development planning stage and favoring the planification activities. As you may see on the right-hand side of this slide, there's just a couple of indicative factors in terms of an economic perspective on how much this technology may be a useful asset for engineering projects. Under these assumptions, the Smart Bay platform may mount up to 3 different sensors for a single acquisition. Over the years, the technological suite has grown, and therefore we have included in our sensors package full frame RGB aerial cameras, compact MW infrared high definition thermal cameras, and multispectral cameras. Going a little bit more in detail on the case studies that we have analyzed, in particular, the corridor mapping is defined as a single pass corridor using stereoscopic metrical cameras. For such reason, due to a cruising speed of nearly 150 kilometers an hour and using Tecnam P92 planes, which are quite agile and quick, capable of acquiring a certain conduct in a linear trend with a turning radius of 500 meters, such fleet and such aircrafts have been ideal for the acquisitions of highways and railways infrastructures. Instead, mounting high-resolution devices such as Phase 1 cameras, IXM-RS 150F, having nearly 150 megapixels of resolution in a 50mm focal length, the aerial acquisitions may favor the monitoring of any kinds of urban or rural environments. As you may see in the right-hand side of the slide, we have projected a couple of indicative factors concerning the ground sampling distance and thus the resolution acquired at the different overflight speeds and flying altitudes. Hereby, typically, the images acquired are then post-processed, allowing to extract several thematic maps and contents as dense point clouds, 3D meshes, digital surface models, and orthomosaics, which are highly used nowadays for the applications in the civil engineering and environmental engineering practices. Instead, for what concerns the thermographical applications, FLIR cameras have been mounted upon our aircrafts, typically for thermal dispersions detections occurring from buildings, for the identification of anomalies and failures of large heating systems, for the evaluation of environmental impacts caused by industries, and furthermore for the prevention and monitoring of forest fires. In such a sense, last year we have conducted a very strong and intense campaign with over 450 hours of flight, acquiring over 800 solar panels across Italy, as you may see on the right-hand side of the slide. The thermographic inspections therefore permit the identification of the faulty cells of the solar panels, allowing a rapid intervention in repairing, restoring the correct functionality of the panel systems. Instead, this year, during the colder months, it has been possible to monitor the district heating of the city of Turin. In this case scenario, through a couple of acquisitions conducted during the colder hours and thus the night, it was possible to monitor the entire network of heating systems across the city, allowing some punctual inspections in order to identify the leakages occurring. Thanks to specialists in the thermographic field, the analysis of the entire network has been performed, and the repetitivity of the surveys permit also to record a time series of events, reducing costs of inspections and favoring the urban planning activities. Moreover, multispectral analysis have been included by means of a Maya S2 sensor, which is a device having the same bands as Sentinel S2 satellites, capable of producing NDVI maps and recognizing vegetation vigor and crops health with a higher level of detail, typically less than 1 meter resolution when compared to satellite data, as for example 10 by 10 meter grids. Nowadays, Digisky has been focusing a little bit more on the SAR radar activities. Therefore, partnering with MetaSensing, we have embarked upon our planes synthetic aperture radars devices having lightweight, compact size, and low power consumption, avoiding any aircraft aerodynamic design to be changed. Hereby, working with multi-channel and frequency systems, it has been possible to acquire approximately 6 acquisition strips of 40 kilometer length within solely 1 hour flight. In particular, the two types of radars we've been focusing on are the METROLOGY X-band, which has typically an accuracy of 25 centimeters and can send imaging, mapping, interferometry, and geointelligence. And furthermore, an L-band SAR radar, which is capable of furthermore providing some details below the ground, having a penetrating ratio of acquisition also reaching 2 meters below the ground surface. It is possible to detect water leakage and furthermore evaluate the subsidence phenomena of the ground. Furthermore, during the years, it has been possible to embark upon aircrafts in the Smart Bay technology, hyperspectral cameras, and LiDAR technology. For such reason, the market competitivity that has been brought by Skymetry has been the reduced costs thanks to the optimization of the monitoring technologies using aircrafts and drones, an accurate flight planning with immediate interaction with local and avionic authorities, a high productivity acquiring within just 1 hour time over 1,000 acres or 50 linear kilometers of land. We have been possible to provide restitution of high-resolution digital maps and informative documentation complementary to the acquisitions already performed by the satellite with a greater level of detail and resolution. For such reasons, we believe that Skymetry may be a new frontier in the aerial monitoring systems, and we wanted to share today this brief presentation with you. For such reason, on behalf of the Digisky team, we thank you all for the attention, and for any further questions, don't hesitate to contact us. Thank you.
Thank you, Luca.
Thank you.
We have 2 more minutes. Can you show us a 3D model?
Sure.
Of
yeah,
road,
only 1 second.
Highway. What do you prefer?
Okay.
And how the platform could be used by a third company to get solutions for problems like the...
Sure. Only 1 second. Sorry. Okay. So I'm going to show you a couple of projects we've been developing lately. This has been an aerial acquisition conducted on Livorno's port, and the main goal was to integrate within a platform all web GIS contents, recalling the available data present on the geoportals, as well as some integrations for the identifications of obstacles present at site. As you may see in this 3D model, you may find the positions of each camera frame that has been shot within nearly an hour and a half of a flight, covering over 2,500 acres. For such reason, it has been possible to generate a digital model in terms of 3D components. What you may see right here is a 3D dense cloud, illustrating both the port of Livorno, a part of the city center, and the areas for which we have an exchange in a commercial way of cargo. For instance, it has been imported in the following context: all the elements characterizing the infrastructure of Livorno in order to enrich the dataset, and furthermore, in order to identify and obtain a greater level of detail, it has been possible to include a campaign of topographic assessment of points, which may give a greater position in reality to the models that are generated from aerial acquisitions. As you may observe, the levels of detail of our imageries, as mentioned, are quite substantial. They reach approximately 2 to 3 centimeter pixel. I don't know if it may be clear. And these high-resolution images may be quite useful for the planning and the design, for example, of bridges, infrastructures. Furthermore, monitor the ships that are incoming into the related port. Other alternative applications have been, for example, the monitoring in the hydrogeological fields for what concerns the projects of constructions of um, sides for the corresponding riverbeds in order to prevent flooding. In the present consideration, we have developed an acquisition both in the summer period of time and furthermore in the winter period of time in order to evaluate some change detections caused by the vegetation. In such case, the main goal of the present acquisition was to evaluate the areas of the river which are more prone to flooding. Therefore, in order to generate some projects, in order to put in safety the population, therefore having an application in the civil protection environments. As you may see, we typically integrate the context and WebGIS data with a platform called Pangea, which allows us to extract also contents. For example, extract strips of dense point clouds, which are 3D elements, which allow to investigate the profile of the territory being monitored. These contexts may be then imported into a certain AutoCAD platform in order to perform some vectorial data and cartographic acquisitions to then furthermore design civil projects for use and civilian use applications. Unfortunately, I don't have many other projects available right now, but I hope I gave you an idea.
Thank you. I appreciate very much your presentation. And thank you.
You're welcome.
Are there any questions?
Thank you for.
Okay. Next speaker. Thank you very much, Luca.
Thank you. Goodbye.
See you. Bye-bye. Next speaker is Lieutenant TENACE from Poligono Salto di Quirra. He's a young engineer.
Good afternoon, everybody. I'm the Lieutenant Pasquale from Poligono Interforze del Salto di Quirra, Italian test range of Italian Air Force. Today, I'm going to speak about the use of multi-frequency Doppler radar for space surveillance and tracking activity. Let's have a look at the summary. I will make a brief introduction. Some characteristic of Mfdr sensors, some tracking operational procedures, and a description of operational events. Let's go. The Italian Joint Forces Test Range is located in Sardinia, in East Sardinia, exactly in Perdas de Fogo, since 1956. The main purpose of the PISQ is that to experiment all weapons like bombs, rockets, and missiles. But the PISQ is also a site for training. In fact, we have ground activity, naval activity, and air activity from all armed forces in Italy. When did the activity of SST started? In 2080, with uncontrolled re-entry of the Tiangong-1. The PISQ was experimental involved with our sensor, the Mfdr. Why I say experimental? Because the radar system was not conceived for this particular activity, but only for normal operation that we have at PISQ. And we speak about a range of 40-50 kilometers. Instead, in space, we speak about more kilometers. So after the successful campaign, with the good results we obtained, the European consortium decided to include the PISQ as a major tracking site for the SST activity. The Mfdr Sensors is produced by Weibel Denmark and is a doppler solid-state radar. We have 4 sensors, 2 medium range with nominal gain of 42 dB and transmitting power of 320 watts, and 2 long range with nominal gain of 45 dB and transmitting power of 640 watts. The system is a continuous wave, has a multiple feeding microstrip based on subarrays of 8 for 8 degrees for the medium range and 16 for 16 degrees for the long range. The system, the radar, has also software for conduction and post-processing procedure called WinTrack. In WinTrack is implemented a basic function that permits to predict the orbit starting from a two-line elements, TLE, or from a state vector. How is the operational procedures? We received the task by our National Space Surveillance Operative Center, as identified with the Space Surveillance Award Center of Poggio Renatico. And we verify the feasibility of the task, because the task was as not to overlap with the other activity. Then there is the propagation of TLE to predict the orbit and to correctly set the radar. After the propagation, the measurement starts, and the collected raw data are shared with my section, the data processing center. We make the post-processing and the extrapolation of the clean track, and we send it to the ISOC to be shared with the other SST partners. Let's have a look on operational event. The event consisted in a launch and docking of a space vehicle. The sensor we used was the Mfdr long range, and we were able to track only the docking because of our geographical position. In this picture, you can see that there is a dark strip. What does it mean? This dark strip means that the radar was operating in a continuous wave. In the other part of the picture, the radar was operating in frequency modulation. In the upper right corner, there are 2 lines, and they are not aligned. So we supposed that they were 2 different objects. But there is also a gap between these 2 lines. And how we can determine what is in this gap interval? By applying the motion compensation. And the result is the following. Now you can see 2 traces, but in the next one, I highlighted it, and the green track is the space station. Instead, the red one is the capsule, the spatial vehicle. And on the right part of the image, you can see that they are converging at the same point. If we zoom in, we can see better that there are many points, but the traces are also noisy. So how we can distinguish what is a good point and what is noise by applying the fitting. In result, we have the azimuth, elevation, and radial velocity correlated with time, and these are the results that we share with other partners of European consortium. Thank you for the attention.
Thank you, Pasquale. I appreciate very much your speech. Is again an opportunity for the Air Force to present to the other colleagues what's going on radar or on sensors. Thank you very much. Any questions? Great. We are at the end, quite at the end of the military panel. We are waiting Lorenzo Porcelli. I don't know if Lorenzo is on the web call.
Yes. Hello. I'm here. I don't know. Can you hear me?
Yeah. Lorenzo, okay. Good afternoon. Lorenzo is a young engineer. He graduated last year at Politecnico di Milano in aerospace engineer. Now he works in a Spanish aerospace and defense company, GMV. And thank you very much for your speech, Lorenzo.
Okay. And I'll, yes, thanks for the permissions. Okay. Okay, can you see the screen?
Yes.
Okay, so welcome everybody. So I'm Lorenzo Porcelli. I'm a junior aerospace engineer in GMV Madrid. And today I will make a short presentation about space surveillance and tracking activities, which I'm sure you are already aware of because we had a very nice presentation about them before. But I hope you'll enjoy the presentation. And just to start with the content, I will introduce the space environment and the space debris problem. Then the risk of collision events as a way to introduce space surveillance and tracking. What are other space surveillance and tracking activities and instrumentation required for it? And finally, an overview of some of the SST programs in Europe. So, as we already know, space activities have been thriving in the last year due to the technological development and progress, and also because of reduced launch costs, because we are seeing reusable and smaller launches, and also small satellites are becoming quite popular, and they are very cheap. And in fact, this is reflected in the number of launches per year. We can see that there was a peak in the 70s and 80s in the golden age of space exploration, then a steep decline in the 90s and 2000s, mainly due to the collapse of the Soviet Union, but the trend is rising again. In fact, we can see that the numbers are increasing and they are expected to be skyrocketing in the following years. And usually objects in space are divided according to their altitude, defining some regions. And the most crowded one is for sure low Earth orbit, or LEO, up to 2,000 kilometers in altitude. It is the left bar in the right plot of the slide. And you can see that most of objects are there. And another very popular one is GEO, where usually telecommunication satellites are. And it is the second bar in the plot, but also the third one, which is EGO, Extended Geostationary Orbit. And please note that these numbers are only for detected objects in space, because detection of objects in space is quite a problem, as we will see. And however, one of the problems is that the majority of objects in space is not functional. So they do not have any capability of operations and also of maneuvering. And they are usually called space debris. And debris can be, for example, payloads at their end of life, dead rocket bodies, mission objects, or objects coming from fragmentation events, which is when something detaches from another object, creating another object as well. And these events can be deliberate. For example, there were some of them one in the 60s, the Westford copper needles, which were released in Leo for a US radio frequency experiment, or from the Soviet Union, which released some nuclear coolant from the Rotsat, which were nuclear reactors in the 80s. But fragmentation events, of course, can be also non-deliberate. For example, there can be terrain wear of satellites, but also collision events. And here you can see a small plot of the source or nature of objects in space, according to the ESA Discos catalog, which is a database collecting information about objects in space. And you can see on the right side that objects coming from fragmentation are the most popular ones. We can see some rocket bodies and mission objects. Payloads are estimated to be around 8,000 units, but this number considers both active and non-active satellites. Active satellites are around 6,000. So if we consider all of these numbers, sum them up, it is clear that space debris is the major actor in space. And why can that be a problem? Because, of course, debris cannot be controlled nor maneuvered, so it's basically orbiting in space. And this increases the collision of risk with other debris, but as well with operational satellites, which is something to be avoided at all costs because of many implications. A collision can completely break up a satellite, or it can damage it permanently. And the higher the collision risk, we are expecting to have more collision events. And if we have more collision events, we are expecting to have more debris. So the circle completes. And this is, let's say, summarizing what is called the Kessler Syndrome. So this cascading effect of the generation of debris. And just to mention some of the biggest collision events in history, there was an anti-satellite or ASAT test on the Chinese Sungyun in 2007, from which over 3,000 fragments were generated. There was a collision between the Russian Cosmos 2551 and the Iridium-32 in 2007, from which over 2,500 fragments were generated. And the latest one was in November 2021, with another ASAT test on a Cosmos satellite, from which 500 fragments were generated. But they are still counting them because they couldn't find them at all. So we are expecting these numbers to increase by a lot. And so how can we predict these collision events in advance, and so eventually take measures to avoid them and guarantee the safety of space operations, so the integrity of operational spacecraft? And this can be done by assessing conjunctions between objects and computing the probability of a collision. And this can be done by constantly observing these objects and predicting their trajectories. And this is basically the foundation of space surveillance and tracking activities. So let's say I introduce collision events as a way to talk about space surveillance activities, space surveillance and tracking activities, because of course there are other activities in this discipline. For example, there is cataloging, because of course when we detect some objects and predict their orbits, we would like to keep a register of it in order to, let's say, have a greater awareness of the environment. There is design of collision avoidance maneuvers, which are actually the tool to escape conjunctions and collision events. Re-entry prediction, of course, to avoid any catastrophic re-entry on Earth, as it was mentioned in the last presentation with the Chinese space station. Support in launch and early operations phase of space missions, and other activities, for example, fragmentation detection, as well as maneuver detection, which is actually the topic I've been focusing more in the last months. And what is required for space surveillance and tracking? Of course, a network of sensors, which can be both Earth-based and space-based, even if space-based systems are, let's say, still in development. And instrumentation, as you might know, can be optical, so usually telescopes and satellite laser ranging stations, radio frequency instrumentation, so radars, but also other means can be used. For example, global navigation satellite systems, as well as other sort of signals obtained by payloads. For example, telemetry can be used in passive ranging. And here, an example of a space surveillance network. It is the biggest one in the world, and it is led by the 18th Space Control Squadron of the United States Space Force, and it's called Space Surveillance Network, or SSN. And you can see that they have a sensor displaced all over the world, as well as some cameras on orbit. And just to mention some other things, of course, this is trivial, let's say, but better instrumentation and calibration of sensors leads to better SST products, because, of course, with higher accuracy of measurements, we can estimate orbits better, as well as the uncertainty associated to the estimation of the state. And so we can compute conjunction assessments or probability of collision between two objects better, as well as having more accurate T predictions, for example. And one other thing to mention is that we were talking about objects in space. I showed you some numbers, but actually they are expected to be way more than that, because there are some objects that at the current technological level cannot be seen. And they are usually debris below the dimension of 10 centimeters. And this is quite a problem. Right now, let's say the state-of-the-art method to treat this object is to have statistical model to generate this population. But I think there are technological, let's say, there is a technological progress way in order to be able to see these objects in the future. And just to mention how SST is done in Europe at civil level, there are, let's say, two major programs, I would say. The first one is called Space Situational Awareness, which is now part of the space safety program by the European Space Agency. And this program includes SST, but also SWE, which is space weather, which studies, let's say, sun activity and its interaction with the Earth, but also a NEO segment, which studies near-Earth objects, so basically asteroids. And this is mainly supported by ESA's own network of sensors, but there are external partners collaborating. And another program is USST, which is supported by European Commission. And this is a cooperation between 7 national space agencies, Germany, Spain, France, Italy, Poland, Portugal, and Romania. And there is a centralized satellite center, which is EUSATCEN. And basically, each country makes use of its own network, then data is shared so that SST services can be provided to users. So USST is actually a service provider. So satellite operators can sign a contract with them and they provide services. And other initiatives, for example, there is the SST program by the UK Space Agency, UXA, or there are USTM and SpaceWiz, which are still funded by the European Commission. And they focus actually more on space traffic management, which I would say is some greater framework in which SST included, which also includes definition of flows for managing traffic in space. And in the end, just to make an example of USST, how let's say, ISST service provider works. And for USST, let's see, there is on one end the sensor, the network of sensors operated nationally, which take measurements of objects and usually correlate them in order to have, let's say, measurements from the same objects. This is then used in the data processing part in order to create the databases and catalogs of objects in different orbital regions, LEO, medium Earth orbit, and geostationary orbit, which are then shared to a common USST database. And from them, there are also tracking requests as well as tasking requests for the sensors. And finally, data is used to provide services. And USST at the moment provides 3 types of services. There is CA, which is conjunction assessment, so for collision events, RE service, which is for re-entry prediction, and FG service, which is for fragmentation detection. And these services are usually provided to the users via front desk, which is represented by the EUSATCEN. But in the case of high interest event of collisions, there is a direct link with the user, so in order to inform them of the threat. And for example, my company GMV is part of the CA service, so it provides software and, let's say, workforce for USST in this way. So let's say this is it, this brief introduction. I hope you enjoyed it, and so thank you.
Thank you, Lorenzo. I appreciate very much your presentation. I found some parallel related to the space situational awareness that before Colonel Galgani presented the policy of the Italian Air Force. Are there any questions? No. I would like to thank you very much all the speakers for these days where has been presented the new technologies inside the Italian Air Force, but not only in the Italian Air Force, but also at the Navy. Thank you very much for all the speakers, and I hope to see you again next year. Thank you. Bye-bye.
Thank you very much. Bye. Goodbye.
Ciao Lorenzo, thank you, bye.